Okay, so let's do an extended Euclidean algorithm. So let's calculate greatest common divisor of 4,321 and 1,234 together with, let's say, call it B, and together with two integers x and y such that D equals to 4,321 x plus 1,234 y. So let's see, let's try to execute the algorithm as we discussed in class. So the table will be remainder quotient x and y. Okay. The first two rows is just data entry. So the big number is 4,321. Small number is 1,234. We didn't do any division yet, so nothing here. And then we initialize the vector xy with 1, 0, and in the second row, 0, 1. Like we discussed, the meaning of every row is the number in the R column is equals the number in the X column times 4,321 plus the number in the Y column times 1,234. So 431 and 1234 are just labels for the columns of X and Y respectively. Okay, so there's the data entry. Well, let's don't count the head of the table. And then let's try to start the algorithm. At every step, the algorithm consists of dividing the big number by the small number with remainder. So how many times enters 1,234 in 4,321 enters 3 times. And multiply 3 times 1,234, subtract from the big number and find the remainder, and the remainder is 690. Now, very important how to update the xy vector. Multiply by 3 the last written xy vector, like multiply a vector by 3, multiply every component by 3, and subtract from the previous xy vector. So basically, we can look at it this way. Multiply every entry by 3, subtract from the entry above it. Multiply by 3, this one, subtract from the value of the y 2 steps before. So how to update now? It's 1 and minus 3. How to read this row? 619 equals to 4,321 times 1 minus 3 times 1,234, which is exactly the substance of this division with remainder of the big number by the small number here. Let's continue, do the same thing over and over and over again. That's the idea of algorithm. So, until when? We'll do it until the entry in the R column remainder gets to 0. So let's see. How many times enter 619 in 1234? So only one time, it barely misses 2 times, only one time. Was the remainder is 650. Update the xy vector. Multiply by 1, subtract from the previous one, get a minus 1 and 4 here. Okay. Divide the big number by the small number. So how many times there? 1 time. Remainder is 4. Multiply and subtract, we get 2 and minus 7. Okay, one more time. How many times enters 4 in 615? Is well, 4 in 600, 150. 4 in 15, 3 times. That makes 153. and the remainder is 3. Okay, now multiply and subtract. 153 times 2 is 306. Subtract from minus 1 is minus 307. 153 times minus 7 minus 1050, 1071. So minus 1071 subtract from 4 is 1075. Okay? Okay, let's continue. Divide a big number by a small number. How many times in the string? 4, 1 time, remainder 1. We get 309 here, because multiply by 1, subtract from minus 307 from. From is a keyword here. Subtract minus 307 from 2 is 309. So here multiply by 1, subtract 1075 from minus 7 is minus 1082. Finally, let's see, divide the big number by the small number. How many times under 1 and 3? 3 times. Remainder 0. Therefore, at this moment we close the shop, and we can state clearly the greatest common divisor of 4,321 and 1,234 is 1. So D equals to 1. In other words, 1,234 is relatively prime with 4,321. Right? And the formula is, the conclusion is, let's see, D, which is 1, is 4,321 times x. The value of x here is 309. Plus 1,234 times the y value from here times minus 1,082. It would be well nice if you just double check and verify this identity and the result of this apparently messy calculation is exactly the GCD. One of the most important applications of this extended Euclidean algorithmic cryptography is to find inverses modulo M. So to find, let's see, A inverse in Zn. So we have to execute the extended Euclidean algorithm for big number M and small number A. And then in this case, for example, if we want to find the inverse of 1,234 modulo 4,321, this will be the M value and this will be the A value. And the inverse of A, provided D equals to 1, right? Because if D is greater than 1, if we execute the extended Euclidean algorithm for M and A and we get the greatest common divisor greater than 1, we declare A not invertible. But if D is 1, the value of A inverse is just the entry Y pending below A. So in this case, what can we say? 1,234 inverse equals to minus 1,082 in Z sub 4,321. So the inverse of 1,234 modulo 4,321 is minus 1,082. Now, most people like positive numbers, at least positive looking numbers. There is no negative and positive in modular arithmetic, but we can make them positive looking. How to make a negative looking number positive looking? Just add a suitable multiple of 4,321, which is the modulus. Adding or subtracting the modulus means nothing because modulus is 0, modulo 4,321. So while the modulus is 0, the appearance may change to a positive number. So this equals to minus 1,082 plus 4,321, which is 3,239. So this will be the inverse of 1000, the standard inverse of 1234 modulo 4321. So this is one of the two most important algorithms in cryptography, modern cryptography. This will be extended Euclidean algorithm. So as for the speed of the extended Euclidean algorithm, let's see. Let's discuss one important result. So if we want to execute the extended Euclidean algorithm for big number A and small number B, we have a theorem, which is the Lame theorem, saying that the number of divisions is at most 5 times the number of digits of the smaller number. So that's a pretty effective algorithm, because if you are working with numbers which are, let's see, 200 digits, we have to do at most, let's see, 5 times 200 is 1000 divisions, which is, for a modern computer, is just an easy task. Okay. So much about one important algorithm in cryptography. Next, we'll discuss about the other important algorithm, which is fast exponentiation.